Hey, hi there. So we have finally arrived to the inferential statistics module, and we'll be starting off with hypothesis testing session 1. So we have divided the entire hypothesis into 4 to 5 parts. Today is the first session, so let's start from the basics. So whenever we talk about hypothesis testing, the first thing which comes to my mind is why do we need to do it? Okay. What is it dependent on? Right? Any kind of inferences which you draw from data requires a robust analysis, a robust understanding. What I'm trying to say is, if I ask you, giving an example again, the average price of any commodity in the market, and if you have a data sheet, and from the data sheet you have calculated some value, but is that mean value absolutely correct with the market standards? Where was the data collected from? Is the data which you have in your hands in the form of an Excel sheet or in the form of a server or whatever it is it appropriate? Is it correct? Is the source correct? Because that only represents a sample of the entire population or universe. That is why we first need to understand the need for sample. So that is a sample data which we have extracted to make our job easier, because collecting data points from population is not possible because of two factors. One is the time factor and the other one is effort factor. To make our analysis robust, to make sure that our data is accurate, the best thing would be to draw to collect the data from the universe on population, but that is not possible because of these two factors. That's why when we extract samples from data, we have to be very, very careful. And if you are not extracting it, if we already have a sample data, we need to perform some rigorous tests to make sure that whatever data we are using is appropriate and it will help in our analysis. Okay. So, of course, to extract every data point from population is not possible because of time and budget constraints, effort as well, right? It's not possible to collect, every data point. Maybe it will take, say, 7 to 8 years of our lives, but that is not worth it, right? So, therefore, a sample of the population is drawn so that we can make inferences about the whole population. Whenever we extract sample, please understand this. Although we calculate the sample mean and standard deviation, my ultimate goal is to draw inferences on the population, not on the sample. So my motive is to make sure that my sample adequately represents my population. That is what my goal is. Okay. And if it does not, what are the steps I can take to ensure that? So the purpose of sampling is to collect data that adequately represent the population. But sampling will have some unavoidable and unintentional errors. Can we avoid them completely? So there are So what I'm trying to mean by this is that, but if you look at from a human perspective, whenever we are collecting data, be it manually or be it randomly, be it through some mathematical technique, there always will be some unavoidable errors inside it, unavoidable bias towards it. We won't be able to avoid it completely. To take into account these unintentional errors or unavoidable mistakes, we do hypothesis testing. So basically, when I give an example in the previous few videos about the average price of rice in Bangalore, we said it's rupees 50. But is rupees 50 correct? How accurate it is? To answer those questions, we have to do hypothesis testing on the assumptions or on the inferences which we have or parameters which we have calculated from the sample. That is called as hypothesis testing. Hypothesis testing is done in almost every domain in the world today. Starting from medical industry, rigorous hypothesis testing is done in the medical industry to check the effectiveness of a dose on a particular disease. Right? We talk about the financial sector, you talk about automobile sector, even traditional industries, right up to the investigative departments, crime departments. Everywhere hypothesis testing is done, because whenever we try to collect some patterns, the pattern is drawn from a sample, and I have to make sure that that particular sample is adequately representing my population. Why? because tomorrow my sample should not show a change in behavior. It should show the exact same characteristics, almost near the exact same characteristic like the population. It won't be exactly same. I know there will be some error, of course, but we have to minimize that error as much as possible using hypothesis testing. So it's a test which is done on the assumption about a certain characteristic of population. So we have derived certain characteristic, and it's an assumption, of course, because we have done it based on a sample. So we have derived, say, a characteristic from a sample, and that's an assumption because we are dealing with a sample, and the test is done on that particular assumption which we have created. To give you an example, what is the price of rice in Bangalore, right? We say around, it will be around 50 rupees per kilo, okay? And around means what? You're taking the average value by going to say 100 shops. That is where we have to do the test. So there are two kinds of test, or two statements, I would say, in hypothesis testing, which is important. One is the null hypothesis. So there are two statements which are made during a hypothesis testing. The first hypothesis is called as the null hypothesis, and the second hypothesis is called as the alternative hypothesis. Null hypothesis is that statement which does not challenge the status quo, whereas alternate hypothesis will always challenge the status quo. What does it mean? So what I'm trying to say here, once you have derived the information, it's around 50 rupees per kilo. Null hypothesis will support your inference, what you have drawn. Mu is equal to 50, which means that population mean is also equal to 50. And alternate hypothesis will say mu is not equal to, or the population mean is not equal to 50. Mu is not equal to 50. Population mean is not equal to 50. This is how the statements are derived. I know there are a lot of confusion or questions around, which statement should go in the null hypothesis part, which statement should go in the alternative hypothesis part. But guys, please understand there is no such definite way. But it all depends on the problem statement which you are trying to solve. And we'll do a lot of examples, and through those examples, we'll be very clear about which statement should be a part of null or the alternative. Now, before we go to define what is type 2 and type 1 and type 2, as I told you, right, that we would see why there are two errors. Please understand. Let's try to think about it. Okay. Okay. So we have two situations which may happen after a hypothesis test. Two results which may happen after a hypothesis test. And that is, in one case, my null hypothesis will be accepted. Case one. Case two, my null hypothesis will be rejected. These are the two possible outcomes of my hypothesis testing. Now, what are the problems which I can face? Problems which I can face is that when null hypothesis is accepted, either I may be correct or I may be wrong. I may be wrong, right? So here also either I will be correct or I will be wrong. If you look at the wrong scenarios, there are two wrong scenarios which may come up, right? So when I had accepted the null hypothesis, I should not have accepted it. When I rejected the null hypothesis, I should not have rejected it. So type 1 error happens typically when you reject the null hypothesis. So type 1 error will tell you that you should not have rejected the null hypothesis. Type 2 error happens when you accept the null hypothesis. So basically type 2 error is telling you that you should not have accepted the null hypothesis. Okay, that is what it basically means. Now let's go through it. Type 1 error, wrongly reject the null hypothesis. So it happens when you reject the null hypothesis, right? Okay. Type 2 error happens when you accept the null hypothesis wrongly. So when you basically wrongly accept the null hypothesis, right? So that is when type 2 error happens. So this should not have happened. So this happens when you accept the null hypothesis. So whenever you reject null hypothesis, you have to think about type 1 error. When you accept the null hypothesis, immediately you have to think about type 2 error. The type 2 error is there inside it. So what are the reasons for these type of 2 errors, right? Very simple. As I told you, my sample, although I'm saying that, I got a mean, although my null hypothesis may be say correct, mu is equal to 50. Sample is also 50, mu is equal to 50. but it may be that my sample, the calculations which I'm doing, right, itself is based on sample data in a hypothesis testing, right? So my hypothesis test is not full-fledged, it's not fully correct. There will be errors inside it, and there are other options, of course, when sampling techniques may be fault. I have selected a sample which is not a representative of the population. Of course, those things are definitely there. Along with it, the parameters which I have calculated from the hypothesis test is based on the sample data. So we are not completely devoid, or we have not completely escaped from the uncertainties in my. Okay. Now I want to give you an example. Okay. So let's say you are a judge. You're a judge in some court, and there's a man on trial. Okay, a man is on trial. So he's in the courtroom. He's facing uh, some trial. Okay. So what would be the null hypothesis and the alternate hypothesis for a judge to establish for the person? Okay. So if you look at the null hypothesis, it will say that the man is innocent, because in the criminal law, a man is always innocent until proven guilty. So my null hypothesis is innocent. You must have watched this statement, listened to this statement in movies. Alternate hypothesis will say the man is obviously. Now, what kind of errors which may be involved? There are two errors, right? Especially when a man was actually innocent, but we have but judge but you have, or the judge has basically mentioned that the one of them can be that the man was actually innocent, but the judge has given the verdict that he is guilty. That is one type of error. Other one is the man was actually guilty, but the judge has given the verdict that he is innocent. Now, which one of them is actually dangerous? Let's see. Man. Okay. This is the verdict. Okay. And this is the actual. Verdict is, say, not guilty, but actually he was guilty. Verdict is guilty, but actually he was not guilty. Which is more dangerous? Now, many people say, ki, oh, the person was actually guilty, but the verdict was not. This would be more dangerous. But no, according to criminal law, it favors human life more. So this is more dangerous, because an innocent guy might go to jail because he was given a wrong verdict. Now, what are different types of errors involved here? Think of it. Man is innocent will come from the verdict. Man is innocent, not guilty. This is where the judge has accepted the null hypothesis. Accept null hypothesis means type 2 error. So this statement is type 2 error. Second statement, verdict is man is guilty, which means that each not has been rejected. Immediately it's type 1 error. Let's see. Innocent man wrongly convicted, a guilty man wrongly acquitted. Type 1 error. Type 2 error. Innocent man wrongly convicted. So innocent man wrongly convicted. So he was proclaimed to be guilty, which is the second case here. So this will belong to type 1 error and type 2 error. Very simple, guys. So this is how you can use certain examples to clarify all your doubts, strengthen your concepts, so that it will help you in the further, more comprehensive concepts and analysis. Now the main question is, how do we make the decision? Which one to accept? The null hypothesis or the alternate hypothesis? And we do that with a very simple comparison. Okay. Either we can compare the test statistics with a critical value, or we can compare the p-value with alpha. Okay, now what are these values? P-value, alpha, test statistic, critical. That is what we are going to now slowly learn in the next few slides. So there are different kinds of hypothesis tests which we can do, okay, based on a type of data, based on the information which is available. But The process, the step-by-step sequential process is exactly the same. Now, please understand, guys, this is again for theoretical purpose, to give you theoretical understanding, right? Especially if you're in a school or institution, you'll be able to relate to this and you need this. Whereas people from the corporate, okay, just understand the concept, because there are all these steps which we'll see, 4 to 5 steps, can be easily achieved by one single line of code in Python. So we'll do that as well. So please do not forget to check out my the application video of hypothesis testing. Okay, so the steps which are common in every test. Step one, what we calculate a critical value. What is this critical value? I'll tell you in the graph. We'll try to visualize this and understand. But let's go step by step. We calculate a critical value, and the critical value is nothing but we calculate the and this critical value is calculated from a table using alpha. Remember in the previous slide we understood alpha, critical value alpha. So the alpha is nothing but the assumed level of significance, the assumed error. I am 95% confident, 5% there may be a chance that my hypothesis is wrong. That 5% is alpha. And using alpha and one more parameter which is called as degree of freedom, DF. From a table, we extract the critical value. So critical value extraction is kind of a manual stuff, because we have to query the table and get it done. But please understand, all these tables and everything is not required when it comes to Python. We'll have a function. I'll show it to you at the end of the video today. So we are already acquainted with tables, right? We saw the Z table, normal standard table, right? How to calculate the probabilities. So similarly, we have tables for calculating critical values also. We have certain distributions, we have certain tests like t-test, z-test, chi-square test, and all of these actually have their own tables where you can calculate the critical value. So the critical value for every test we can calculate from the respective tables using alpha and degree of freedom. Alpha is something we assume, right? Degree of freedom is something which we calculate from the data itself. Okay. So if you remember in standard deviation, while calculating standard deviation of sample, in that lecture I told you, we divide it by n minus 1, right? Standard deviation. We use n minus 1 for sample standard deviation. That n minus 1 is actually degree of freedom. So degree of freedom is calculated from the sample data, because it's number of data points minus 1. That is how degree of freedom is typically calculated. Okay. So in the first step, my critical value is calculated from alpha and df. Alpha is something which we assume. Degree of freedom is something which we calculate from a sample. So there is no dependency here, but both of them combined will give me the information of xc or critical value from a table. So it is a table where we'll have all these information. Okay. Step 2, we calculate the test statistic. Now this is very important. Test statistics is calculated from the sample itself, from the sample. So this should have been sample, calculated from sample. Okay. So that calculation from sample is nothing but it's dependent on what we have in a sample. What can we calculate from a sample? Either we can calculate the sample mean, the sample standard deviation, or the population mean, population standard deviation, all of these things, and the degree of freedom. Right. So mu and sigma you can see here is from the population. And one may ask me, how did you get population, mean and population standard deviation? These data points are typically extracted from historical significance. If we have them, good. If we do not have them, there's still a way around, because we have other tests which are not dependent on the population mean and population standard deviation. So now where do we calculate these test statistics from? It is calculated from the sample data. From the sample data, we'll already have the sample mean, the sample standard deviation, and the degree of freedom as well, right? Sample mean, sample standard deviation, and degree of freedom can be easily calculated from the sample data. And I've written a function because it's a formula of these parameters, and this formula will keep on changing with respect to different hypothesis tests. Okay, I've written sample mean as small m, guys. You can also write this x bar, no problem. Okay. So step 1, calculate x critical. Step 2, calculate SS, x statistic. What is step 3? Now we have to compare XS with XC. How do you compare? If my test statistic is less than my critical value, or you speak from the critical value perspective, if my critical value is greater or then my H naught is accepted. However, if my test statistic is greater or it crosses critical value, then H naught is rejected. So that is how we arrive at this particular decision, whether H naught is accepted or rejected. Okay, so it's pretty much a lengthy process, right? Especially the first step where we calculate the critical value from the table. I know alpha and degree of freedom we can easily calculate. Alpha is already pre-assumed, right? But looking at the table, going into that and calculating, it's a bit tedious, right? So there are other ways to do that. What is the other way? The easier way. Okay, what we can do is we can calculate the p value and the x statistic. So x statistics we already know, we know how to calculate. P value is something which is calculated from the inbuilt functions of Python using the input data points. So there are certain inbuilt functions in Python which can easily help us to calculate the statistic and something which is called as the p value. Okay, and once we feed in the data points of our sample into that function, it will give us these two values, x statistics and p value. Second step, what we can do is we already have the alpha value with us, right? Because we assume it. Typically alpha we consider it to be 5% level of significance in the global market today in corporate. We do not go below beyond that. P like around 5%. So we are 95% confidence we try to account for. So next step, we can easily calculate p and alpha value to make a decision. So if p is less than alpha, my H naught is rejected. If p is greater than alpha, my H naught is accepted. Too many comparisons, right, guys? We in the previous slide we compared x statistic with x critical. Here we are comparing p with alpha, greater than, less than, all these things, tend to confuse you. But we'll try to evaluate this very easily using diagrams, using proper figures. And if you understand it from that perspective, trust me, you'll never forget it. Always, your concept will be always be very clear. So this is this I follow this way. So this method is the easiest way. Or there is one more method where you can calculate the critical value also. So the critical value which we used to calculate the non-Pythonic way was from the table. But here also we have inbuilt functions inside Python which can help us calculate critical value of x or the random variable using alpha or some other parameters. And then once we have the xc and final step, of course, we can compare the statistic with the critical value. So this condition we already know, we have already seen in the previous slide. But all these greater than equal to sign don't to carry about. So my takeaway is very simple, and that is I generally tend to follow this step, the easiest possible, not even the previous slide. Okay, where I can simply calculate these two parameters, right? My function gives me this two parameters, okay, by default. Then I can use this parameter to compare with the alpha. So to make a decision, either you compare p with alpha or you compare the state statistic with the critical value. Either one of them. This comparison, the Pythonic way, is much easier because it will be able to do that in one single line of code. Right? So why do we have to follow the long, lengthy process which I defined in the previous slide? But that I've defined it, of course, because institutions or in schools probably you will not be able to allowed to use Python to solve your theoretical question papers, right? That is where you need this. Okay, but in the corporate we use in the first two steps. And it's very important that students also understand the application part. So it will give you some kind of a motivation to understand that is how you solve problems in the real world. So you can see here this is a much faster process. So let's move on to have a detailed understanding, okay, of what we had just learned. Just to clear our concepts regarding less than, greater than, what is xc, what is xs, where is it lying, what is p, what is alpha, right? Where do I place these figures in the graph? Suppose this is my distribution. Okay, now suppose if any test you consider chi square or t-test, z-test, all these tests, come from a distribution. They assume that the data points which is with you follow a distribution. Based on that distribution, you have all these formula with the help of which you calculate the test statistics. Remember the function which I put, f of MSDF. Let's say I'm doing a test which assumes this distribution of data points. Okay, so the alpha value which we're talking about, okay, on the it can be on the left hand side or it can be on the right hand side. Okay, I'm just giving an example on the right hand side. Easier. This area is called as the alpha. So alpha is calculated from the right hand side or the extreme left hand side. For now, let's consider the right hand side only. So from right to left for the right hand side calculation, the left hand side left to right. Now this area under this particular curve which you see is my alpha value, which means that alpha is a probability. Area under the curve gives us what? Probabilities. Remember the cumulative distribution, right? Parameter which we're trying to evaluate, right? When we try to calculate probabilities between two continuous distribution, one thing is for sure, this is a continuous distribution. So when you calculate the alpha, the area under the curve will give you the probability, which is the, here in case it is the alpha value. So this value is what we assume. And the point where this area ends gives me my critical value. Now this critical value of x is calculated from where? It is calculated from the left hand side. Obviously, it's a graph. It's a graph. The x-axis will always be in ascending order of magnitude from left to right. Correct? So this alpha value gives me the position of x critical. Or if you're calculating x critical, either way, vice versa, it will give me the probability of alpha value till the end. Entire area from this till the point, end point. So this also is covered, guys. Okay. So basically, based on this critical value of x or alpha value, we get two regions. One region is called as the H0 rejection region, and the other region is called as the H0 acceptance region. So total probability is how much? 1 minus this amount of area is the acceptance region. This is the rejection region. Why we call it rejection region? Because if my XS, right, my test statistics falls in this region, then the null hypothesis will be rejected. If you remember, XS greater than XC, what happened? The null hypothesis is rejected under this condition. So if it crosses this point, suppose it is lying here, right, my null hypothesis will be rejected. But again, if my XS is lying here, which is less than the XC, if XS is less than XC, then my null hypothesis is acceptance. That is why it is the acceptance region. So this region is the acceptance region, this region is the rejection. Clear? Okay. All right, great. We'll take more examples, guys, so don't worry. So when is H not accepted? H not is accepted when typically my XS is less than X critical. This is the point. This is the condition. So if you look at alpha, alpha gives the position of X critical, and if my XS is less than XC, it should be below XC, right? To less than XC, right? Because I told you my x-axis, of course, is from left to right in ascending order of magnitude always. So once I have this, which means that this area which you see is the P value. So area on the curve defined by the X statistic is my P value. Again, to reiterate, just like this area was my alpha value, this entire area will be my P value. P value is given by a XS and alpha value will be given by the XC and vice versa. So if we compare either way, so XS less than XC, my null hypothesis is accepted, or if my P value is greater than alpha, because if you look at the area of P, lesser the value of XS, more the area of P value, and if my P value is greater than alpha, again my null hypothesis will be accepted. Why this reverse inequality is very simple, because my probability is calculated from right to left, whereas my the x parameters are calculated from left to right. It is more the area of a p-value, it means that the excess is actually less than the x, because you are calculating the area from the right hand side, from the extreme point, I would say. Same thing if you reverse in the for the left hand side also, it will happen. But I'm typically in hypothesis testing, we consider that the distribution which it follows is symmetrical, right? Typically, that is what we do, and that is how the comparison. You can simply shift this comparison on the left hand side, you'll get the same result. You'll get the same. These conditions will remain the same. You can try it out at home, no problem. Okay. All right. Great. So XS is less than XC, the area of coverage increases obviously for P. And that's why data point falls in the acceptance region. Very simple. Now, when is H not rejected? Very simple. Alpha, critical value, I got it. Now, my XS is greater than XC, right? So, it is somewhere, suppose somewhere here. So, my P value will be this region only. This is my P value. So, this is my P value, which means what? My P value, two things, right? My XS is greater than XC, means H naught is rejected, or my P value is less than alpha, then also H naught will be rejected. So that is what it is. Very simple. The reverse way. So when XS crosses XC, the area of coverage for P reduces. And that's why data point falls in the rejection region. So this is my rejection region anyways, right? Correct? And hence, so this is the condition which I already have stated in the previous slide. So now you know clearly what is p-value, what is excess, how is it getting calculated, and where it lies in the graph, which condition to pick up under which situation, which decision to make under which condition. Now it will be very clear, because whenever you calculate these values, guys, just draw this mental picture of this image which we are showing, which I am showing in the screen. The curve and the respective locations of these parameters. If you can visualize this every time, you'll never forget it. So that's it, guys. I hope you enjoyed today's session. I've put in all my effort to explain hypothesis testing in the best possible way that I can, because many students do not actually know the application of hypothesis testing. They know the theoretical part probably, but where is it getting calculated from? What happens under what kind of conditions? How do we apply these hypothesis tests in the real world? That is also, there's a huge gap between the theoretical knowledge and the application part. So please, guys, stay tuned for the next videos. Make notes while looking at my videos. If you have any queries, you can reach out to us, and see you in the next video.